Hello, thank you for coming to this talk. We're going to be talking about programming a time machine using an event-based language that uses risk-based testing. So my name's Dave Copeland, and I think we've got a couple of goals here, right? So first, if you're interested in time travel, then you'll get an introduction to the timeline programming language, which is what we use to create flight plans for traveling through time, and you'll be able to start doing that after this talk. But the other thing that I hope we can get out of this is to understand some of the design decisions that we made when creating the timeline programming language. As you'll see, it's a very unusual language. It has lots of features that other languages don't. It's missing lots of features other languages have. And we'll talk about why that is. And I think you can then take that away to think about how you might use some of this thinking for your designs for APIs or libraries or developer experiences, or even if you want to design your own programming language. So timeline is, as I mentioned, an event-based programming language. It's used to program a single journey through space and time. And so it doesn't really use unit tests. Instead, it uses a Monte Carlo simulation to give us some confidence about what is actually going to happen, to tell us what is the risk involved in running the program that we have written. And it's got an extreme focus on observability. It's very important to know what the program is going to do. And when the program executes, it's very important to know what it did do. So before we get too into it, let's just kind of see what it looks like. This is the simplest possible program, so you can get a sense of how things work, right? So when the vortex back through time and space is established, we run our code, which is to disconnect, right? So this is turn on and turn off. We can't print the string hello world. There's no strings. There's no IO. So this is the simplest possible thing that we could do. So to get into this, it's kind of important to understand like what problem does timeline actually solve? There's a lot of general purpose programming languages in the world, and we could have used any of them to program our time machine, but instead we built our own language. So why did we do that? And the answer to that is, right, understanding how time travel works. Now, I'm sure it's been a while since we've all been in high school. Our junior years, we all learned about temporal mechanics. But if you're not working in the field, then you probably don't have it top of mind. So let's do a little bit of a review about how this works, so we can sort of all get on the same page with why timeline exists at all. So hopefully, if you took anything away from your junior year of high school, it is that time travel is space travel. Right, so the Earth is rotating around the sun, right? So we're moving right now. And in 1 year, the Earth will be back, will have done a full rotation, but it won't be in the same place it was a year ago because the sun is rotating around the galactic center. And of course, the galaxy is expanding away from the Big Bang. So, right, everything is in motion. So if we want to go back in time, it's not sufficient just to go back to a certain point in time. We have to go to a certain point in space. So if we want to go where we are right now, a month ago, well, we need to know where we were a month ago in space. So we need to make sure that we travel there. So that's the kind of crux of how this all works. Now, you probably remember the names Neil Bell and Chris Clark. They were the two scientists that created and productionalized the Time Space Manifold, which is what allows us to travel through time. They spent 10 years validating this approach to see if it would work at all, 5 more years making it actually practical. Now, Dr. Bell focused on hardware. We're not going to be talking about Dr. Bell a whole lot, but Dr. Clark is who I worked with. He developed the initial firmware for the time space manifold, and he and I worked on the software that became the timeline programming language, and that's what we're going to talk about here today. So we want to travel back through time, right? So we need to go to a certain point in space and a certain point in time. Now, the problem is how this actually happens, right? So, as you know, travel happens through a vortex. I like to think of the vortex itself as a tube. Now, we don't go through the fourth dimension or the fifth dimension or some sort of wormhole. We're actually traveling through space. We're actually intersecting space as we make the journey. So we're going through space and time, and we're actually physically manifesting there. So the problem is that space has a lot of stuff in it, and that stuff is also in motion, and it's not in the same motion as us. It's in motions different than us, and so we could run into it, right? We could find that things are in our way. So if we think about our tube here, and our blue line is us, and this cube is like some piece of space junk, well, we could run into that. Now, there's an analog, right? So hitting it would be bad, obviously. So there's an analog to how you might fly planes or drive cars. If you're driving down the street, you see a pothole. Well, you steer around that pothole. If you're flying a plane, you might have radar telling you where other planes are. You can avoid them. You might see bad weather. You might fly around it. That works. But that doesn't work for time travel because the trip itself is very, very fast. It just takes milliseconds. So no human can react to what's ahead of them and steer around it, as it were. There needs to be some sort of automated way to do this. So Dr. Clark's first solution was to write a general purpose pilot, right? That's the instinct all of us as programmers have, right? Let's solve the problem generally, solve the problem in a generic way, refine it over time, make it better and better. But essentially, we want to have a single solution that we can apply to all of our journeys. So he wrote what ended up being millions of lines of code and was unable to get the pilot to work at all. It could managed very, very simple risk-free journeys, but as soon as you did something more complicated, it just made it very, very difficult. He was not able to get it to work. So he turned to quite an unusual solution. He thought that a neural network-based machine learning algorithm might be able to do this, but of course, as you all remember, in 2043, neural network-based machine learning algorithms were banned, and due to their inherent unpredictability, their inherent biases, and all the problems that are wrapped up in there, they're no longer allowed in general use. However, the law that bans them does contain an exception. It does allow you to get an exception or a waiver to this law in order to try something that might be of the benefit of all humankind, I believe is the words that were used. So Dr. Clark was able to get a waiver. So he was able to develop a machine learning algorithm to try to create a general purpose pilot. Of course, he basically reaffirmed the reason that machine learning algorithms are banned in the first place. So he was able to create one. Pumping in vast amounts of training data, he created a general purpose pilot, and it was able to successfully navigate a real journey through time. Unfortunately, the second time, it was a disaster. So something went wrong. And it's not necessarily bad that something goes wrong if we can explain why it went wrong and we can correct our system to prevent this error in the future. But this is the problem, because machine learning algorithms are inherently incomprehensible. They are inherently unpredictable. There is no easy way to understand why the journey that failed the way that it did. There's no way to explain the behavior that we had observed. And so therefore, there was no way to improve the system, make it better, and that's not good. You don't want a system that you can't understand, a system that you can't improve and that you can't observe its failure modes and explain them away, right? Essentially, right, machine learning algorithms are impossible to predict, so we can't use them. So Dr. Clark, attempt number 3, he thought, what if instead of this general purpose pilot idea, we forget about that, forget about general, forget about generic stuff. Let's just focus on the specific problems that we're trying to solve. If I want to go through time, I have a specific journey that I'm going to make. I know a lot about that. What if I wrote a program just to solve that one? And after that journey is over, the program goes away. We write another one the second time. Okay, so this had a lot of promise. So we would write a program for each flight, no general purpose anything. If we use a language that makes it obvious how the system is going to behave during the flight, that will help us with confidence about what's going to actually happen. And instead of writing tests, we use a simulation to understand what are the risks, right? No flight through time and space is risk-free, and so we can use a simulator to tell us how risk-free it is, and then make a decision based on the trip itself whether or not we want to go. And lastly, if we can produce comprehensive output about everything that happened during the trip, then if something goes wrong, we have complete information about what happened and can explain that away and improve things for next time. So this leads to the core value of the timeline programming language, which is the most important thing about a program is what it will do. The second is what it did. So from here, all of our design decisions flow. And so the first version of Timeline was created, and the trip was a success. Dr. Clark sent a bottle of rum 100 years into the past. We're not really sure where. He went and dug it up, and on his desk now is a 100-year aged bottle of rum. He samples it on the anniversary of this trip. He does not allow other people to have it. I've heard it's quite good, though. So, okay, that's the problem that we're trying to solve and the general way that we're going to go about it. So let's look back at the programming language again. So here is our hello world. Right, so we can see here that all code is in response to an event. There's no main loop, there's no main function, there's no top level anything. You have to respond to an event. The standard library documents events that might be fired. There's no return values, there's no functions, there's no I/O. All you can do is trigger events. Yes, you can execute computational logic, as we'll see, but essentially to affect what's happening in the program, you have to send events. And there are many events that you can send documented in the standard library. So let's try this. How do we execute this? Well, we could upload it into the time space manifold, I suppose. That would be incredibly expensive. And of course, not all of us have access to a time space manifold. There's not very many of them in the world right now. So we'll use the simulator. The simulator, as I mentioned, will tell us what are the percent chances of success. So when we run our plan, we can see it's pretty good, right? So there's a 98% chance everything will work as expected. 98% chance that the vortex starts up and we successfully turn it off. Now look at these failure modes. There's a 2% chance of failure, and the simulator will break down what are the general types of failures that it's seeing from the simulation. So all 2% in this case are hardware failures. Hardware failures happen. They're impossible to avoid. 1.23% of the time, there's a failed connection. Some hardware failure will prevent the connection from being happened in the first place, and it won't trigger our code, and then nothing works. But this 0.77% is kind of interesting. So this is when we trigger the disconnect, a hardware problem prevents the vortex from being disconnected, and the vortex persists. That uses lots of energy, and we don't like to do that. And we actually didn't really know that this was a possibility at first. The original versions of the time space manifold had no physical on-off switch, and so it was a little bit confusing, right? So we used to do frequent tests, what we call tests in production, where we would open up a vortex back in time around 5 minutes, pointed at the area above the lab where we worked, because you can observe the lab, you can see what was going on there, and you can wait 5 minutes, and if there's nothing there, you know it's safe to send stuff through because there's not going to be any risk of running into anything. So we did this, and then the disconnection failed, which we had never seen before. And so we started scrambling around trying to figure out what we were going to do. You can't just pull the plug on this thing. You have to safely turn the power off and all these things. We hadn't really experienced this, so there's a bit of flurry in the office. And amidst all this chaos, Dr. Clark accidentally kicked his office chair into the vortex. So his chair then traveled backwards in time, 5 minutes, where it was way, way, way above the lab, where it took around 5 minutes to fall back to the earth, hit the top of the lab, started a bit of a fire. So we don't do this as much anymore. The simulator has been refined to allow us to try out more scenarios without having to actually do it for real. When we do need to do it for real, we do it in a much safer way than above the office. We've got a testing facility outside Arizona where we can do this stuff. And the Time Space Manifold now has a hardware off switch that was added just for this case. Okay. Let's see what a real trip is like. So that was just turning things on and off. Let's actually try to plan a real trip. We'll go to the moon as of a month ago. The moon is a great place to go because we've been observing the moon for decades. We know what's up there, which is basically nothing. So there's not a lot of risk going there and running into something or running into people or otherwise messing with the time-space continuum. It's a pretty safe place to go, and it's a really good jumping off point for more complicated journeys. So to do this, we need to have a course. We need to know how far we want to go back, and we need to know basically what is the thing that we're sending through so that the time-space manifold can create the right vortex, point it in the right place at the right time, big enough for the traveler to go through. So for a destination, we use version 5 of the International Celestial Reference Frame. And so this allows us to pinpoint an exact location in space. Now remember, everything is moving. So all of these coordinates are relative to where the sun in our solar system was on January 1st, 2000. From there, we can extrapolate positions before and after that particular event. But we have to have some sort of frame of reference. So the way it works is you can see here there's a plane that intersects the sun, and then there is a line coming out of it that we call an equinox. So we first have a right ascension, which is how far to the right of that equinox inside that plane are we going to go. We have a declination, which is how many degrees above that plane do we want to go. That sets a heading, right? Where are we going in space? And then a distance. How far along that heading are we going? And that it pinpoints us to a location in space. So once we have that, we need to communicate this to the time space manifold. Remember, there's no I/O. We can't enter this in. There's no configuration files. All we can do is send events. So there's an event called trip details that we will send when things start up. And so basically, this event tells the time space manifold, like, here's what I want you to do. Start everything up, get everything going. So you can see here what everything is. I'll explain this code in a moment, but you can see here, these are the ICRF coordinates. This is how far back we're going to go, and then this is a description of the traveler. The dimensions, we just describe a cube that completely encloses the traveler. That's enough for the manifold to figure out how big to make the vortex. All right, so how is this a program? This looks like maybe a hash or a dictionary or some sort of configuration file format, but it's actually code. So let's break it down one piece at a time. So hopefully you can tell by the syntax highlighting that on is a keyword. It's magic. Whatever happens after on, anything that comes after the space after on, is the name of the event. And that event name must be defined. It must be in the standard library or custom defined by you. And this is followed by a bracket, which begins our parameters list. In this case, there's no parameters, so we just have an empty list. And then inside would go our code. Now inside we also have sending an event. So you can also tell send as a keyword. And again, anything after the space after send is interpreted to be the event name. It can have a space in it, so it's nice and readable. That's followed by a bracket that begins our parameters. Now in this case, we're sending two parameters. The trip details event takes two parameters called destination and traveler. The parameters are named. There's no positional parameters. Every parameter has to have a name that the caller must use. And then finally, we tell the runtime when will we like this event triggered. So you can trigger events in the future. You can schedule them. This one just says send this event as soon as possible. All right, so what's going on inside these parameters? Let's look at this construct here. This is a little unusual. Again, it looks like a hash table, but it's actually not. These brackets, they indicate a parameter list. And in this case, they're a constructor of sorts, right? So the documentation for the trip details event says that the destination parameter is of type destination. And destination is made up of an ascension and a declination, both of which are angles, a distance, which is a distance, and a duration, which is a time. So these are all typed. And so these literals, you can see these are typed. And we'll talk about why they work this way a little bit, but you can see the compiler knows that 60 degrees, 23 minutes, 42 seconds is an angle. So this is creating a strongly typed piece of data. So you can think of it like this, right? Okay, so that's the what. That's what is going on here and kind of how it works. But why does it work this way? It's very unusual. All right, so let's talk about some of the language choices. So, we have two examples of parameters with brackets. So in the first case, we have parameters. The second case, there's no parameters, we're using brackets. So consistency is a value of timeline. We don't want developers sitting around trying to decide if their code is beautiful enough to remove the brackets, or if their code is properly elegant so that they need to add the brackets in a certain place or anything like that. Like, that's wasted time. There's no value in thinking like that. We want the programmers to be thinking about the problem that they're trying to solve, and that requires consistent rules that they can follow and not have to think too hard about. So you always use brackets even if you don't have any parameters. We use brackets instead of parentheses because brackets are actually a little easier to type. You don't have to hit shift. They're just a little bit easier. So that's some ergonomics that we rolled in there. Now, despite what I just said, you'll notice that there's no quotes around the event name. There's no strings in timeline, so there's no reason to introduce them just to have some ceremony around the trip details. It's completely clear what part of this construct is the event name. It's everything between the send and the first bracket. You have to have spaces. There has to be a space after send. There has to be a space before the bracket. So it's completely unambiguous what is going on here. So quotes wouldn't really add anything but extra ceremony. And that's no need for that at all. Okay, let's come back to this constructor here because this has got these really strange literals, right? So in a lot of programming languages, if you want to specify an angle, you might just use a float, 32.78. Well, what is that? Is that degrees? Is that radians? What is that? There's no way to know. You have to have some external context to understand what does this number actually represent and how do I interpret this number as something other than a number. And that seems needlessly complicated and confusing and can create all kinds of problems. And when you think about how you talk about angles, as an example, you might write on the whiteboard 60 degrees, 23 minutes, 42 seconds. You'd see that in a paper that you might be reading. You might see that formatted in a report so that you can understand it. So why doesn't the programming language just support that? Well, it does. So the programming language knows that a construct like this is actually an instance of an angle. It's unambiguous. There's no way to look at this and not know what this represents, which is kind of handy. Now, looking at these numbers, right, we'll see that these numbers have commas in them to make them more readable, right? Whenever we look at reports or read papers or see anything that has very large numbers, we see these commas because it can be visually hard to distinguish 1296000 from 1296000. And you can make mistakes, and they can be orders of magnitude, right? This is a galactic scale here, so we need to make sure that it's very clear what numbers we're actually writing. And again, think about writing something on a chalkboard. it should look the same way in the programming language. So not only does timeline allow you to put these commas in here to format large numbers, but you have to do that. You can't write a big string of numbers without commas, without formatting, because that would create ambiguous, unreadable code, and we don't want to allow that. All right, so we've configured our trip. We've told the vortex where we want to go. How do we move forward? How do we write more code? Do we even need to write more code? What is the workflow even like? So in a lot of traditional programming languages, what you would do is you'd use a test-driven development workflow where you would create a specification about how you think the program is supposed to behave. You would write that specification as a series of tests. You would run your code against those tests, and you would write code to make those tests pass. So now your code now does what you think it's supposed to do based on your specification. So with timeline, we're not interested in what the programmer thinks the code is supposed to do. We're interested in what the code is actually going to do. So we use a simulation, and we use a workflow called risk-driven development, which we'll talk about, right? So first, we provide the plan details. That's what we just did. Then we'll simulate the plan. We saw that a little bit earlier, and we'll see that again. That plan simulation will tell us the risks of failure, and we'll assess that risk. We'll say, is that risk one we're willing to tolerate, or is that too risky? If it's too risky, then we need to add code, but we know what the risks are. The simulator will tell us what specific problems are likely and unlikely to happen, and so we'll write code to mitigate the risks that we want to mitigate. And basically, we just repeat that cycle until we have removed enough risk that we're comfortable taking the trip. And when the risk is acceptable, we go. All right, so what's the risk in our current plan? We're not doing anything. All we're doing is opening up the vortex, and what if we just did that and walked through what would likely happen? Yeah, not good. 0% chance of success. That's not a trip we want to take. 100% chance of failure. So we can see that's broken down here. We can see a few new failure modes. So we see the typical hardware failures that we saw before. 98.77% of our failures, though, are dominated by a large object collision. Right, so that means there's an object out there that we're going to run into. Remember our tube in the cube, we ran into that. So that's what's happening. And we can see there's a 90.45% chance that the object we're going to run into is a known object. So what is a known object? So while we can't map everything in the known universe, it's too difficult to know what everything is and where it's going. We do know about a lot of things that are out there. Imagine the Earth has satellites going around it. There's asteroids in the asteroid belt. We do know certain things about where things are, and so we can say with high certainty that where things might be when we take our trip. So in this case, if we ask the simulator for a little bit more details about a particular failure mode, it will tell us what's going on. So in this case, 86 milliseconds into our journey, we're going to collide with a satellite that has a designation 4F76. So we know where that satellite is, and so we have a pretty good chance of running into it during our trip, and we don't want to do that, right? So if our trip is 150 milliseconds, 86 milliseconds in, that's where we're going to encounter the satellite. So we know that in advance, then we can write some code to move around the satellite. So if we look into the standard library, there's a few things that we can leverage here. So there's an event that gets triggered called traveler entered. So that's when the traveler, whatever's going to be going through time, enters the vortex. That starts the countdown. So 86 milliseconds after that is when we're going to run into the satellite if we don't do something else. Now, what is that something else? Well, there's an event we can send called adjust vortex direction that allows us to steer the vortex one way or the other. And so what we can do is we can steer ourselves around the satellite before we run into it, steer ourselves back to get back on course. So this is sort of a visualization of what we might want to do, right? 80 milliseconds into our trip, we adjust ourselves away from where the satellite is. We allow 35 milliseconds for us to get past the satellite safely, and then we adjust ourselves back so that we arrive at our destination with no problems. So let's see what that code looks like. So I'm just going to read this code because it pretty much reads how it says, right? On traveler entered, direction is 45 degrees. Send adjust vortex direction, direction in 80 milliseconds. Reverse direction is 360 degrees minus direction. Send adjust vortex direction, reverse direction in 115 milliseconds, right? That's 35 milliseconds after 80. Okay, let's talk about this code here. So you can probably guess at this line, direction is 45 degrees. That's setting a variable. It's setting the variable named direction. Now we know that 45 degrees is a typed literal. We know that that is an angle. It's not a number, so therefore we know that direction is an angle. The compiler knows all of this stuff. Now, a lot of programming languages use the equal sign to do assignment. Of course, equals in mathematics is for comparison, so that's somewhat confusing. Some programming languages will invent symbols like colon equals or reverse arrows to try to come up with assignment. We figured we would just use the simplest possible thing, which is to use the word is. I don't know if there's any clearer way to say that direction is 45 degrees than literally writing that. Okay, next line of code. We've seen this, this kind of makes sense. You can see here we're scheduling this to happen, not right now, but in the future. Okay, now we can see we're setting another variable called reverse direction, is 360 degrees minus direction. Now we know that direction is an angle because we assigned it the value of 45 degrees. We know that 360 degrees is an angle, and we know that subtraction between angles is well defined, and that produces an angle, so therefore we know that reverse direction is an angle. The compiler knows all of this stuff. Now you might be wondering, we've got a dash in the name of the variable, and we have a dash doing subtraction, like, isn't that possibly confusing? No. So when you're creating a variable name that has multiple words in it, classic languages may have used camel case. Now you remember the studies done out of Stanford that proved that camel case is inherently unreadable and confusing, and so most new programming languages eschew camel case and use underscores. Well, underscores are kind of hard to type. Dashes are a little bit easier to type. With an underscore, you got to get a couple of pinkies there. It's just very difficult. So dashes are simpler, so it reduces mental overhead and increases ergonomics. But you also, in timeline, you can't subtract without putting spaces on either side of the dash. Many coding style guides say, oh, you should put spaces around your dashes when you're doing subtraction to make your code readable. Yes, you should. And why would the language let you do it any other way, right? Timeline does not let you do it any other way. And the advantage then is that we can use this dash to create variable names in a way that is unambiguous. Okay, and our final line of code there. So let's talk about some things that aren't allowed. So you may be thinking, why do we need this reverse direction variable at all? Why don't we just inline this expression 360 degrees minus direction? That would be cleaner, right? Cleaner code, fewer lines, right? Isn't that what we all want? Well, this is not allowed. Parameters have to be either a literal or a variable. You can't put an expression in there at all. Why? So putting this expression in line, it increases the density of the line of code. It increases the number of things happening in that line of code. If you don't understand that line of code, you have to have more context in your head to understand what is actually going to happen and what it all means. So we don't want that. We want each line of code to be as simple as we can possibly make it. Now, the side effect of this is that every expression has a name because you have to assign it to a variable. So this allows you to clearly express what is going on, why it's working that way, and can be very easy to understand what the code is actually going to do. Okay, another thing you might be thinking, programmers, they hate typing things out. A lot of them just don't like using vowels or typing out full names. They want to use like shorter names because that's cleaner or nicer or faster, or you really just don't need to type it all out, or whatever the reasons are. So you might say, let's call this rev direction. Well, this is not allowed because rev is not a word. What does rev mean? Reverse, revile, reverts? Who knows, right? That's why it's not a word, because we don't know what it means. So in a timeline program, all the variables have to be made up of words that are in the dictionary, joined by dashes. Now you can add new words, right? If you want to use a word that is not in the dictionary, you can do that, but you have to define it. You have to add it to the dictionary. And so the upshot of all this is that every single variable everywhere is made of words that are defined in the dictionary. So there's no ambiguity about what some string of characters means. You can look it up in the dictionary to understand, and everyone can stay aligned on what things mean. Okay, let's run this now, right? So we've avoided the satellite. Let's see what happens. Okay, 62% chance, that's pretty good. We've increased our odds. Maybe if we were sending a bottle of rum back, this would be fine. We've got plenty of bottles of rum. If things go wrong, we can just send another one. But if we're gonna send people through, I don't know, that seems pretty risky. So let's look at what's going on. So we can see that 34.7% of our failure modes are what's called a small object collision. So there's lots of little, bits of junk in space, little asteroids, little rocks, things that we just can't track, but we have a statistical understanding of where they might be. And so we can say with some certainty, given any area of space, what are the chances that there's going to be some space junk in there? And we apply that model to our simulator, and that's what's going on here. So it's very similar to um, what we have with the satellite, except that we don't know where the object is going to be. We don't even know if it's going to be there. We need to be able to react a little bit more dynamically. So that means that we need to know kind of what's ahead of us before we get there so that we can make adjustments. So we're able to send a ping that will go down the vortex to see if there's anything ahead of us. And if there is, it will send telemetry back to us, telling us how many milliseconds until we run into this thing. Where is it along the tube of the vortex, and about what size is it? So if we can receive this telemetry, we can then take some action, right? So ping is in the standard library. We can send that whenever we like. Ping will trigger an event called collision imminent. And you can see the parameters here that are given to you when this gets triggered. Okay, sending the ping is relatively straightforward. We can just do that in the traveler entered event. As soon as we get in, let's send a ping so we can get telemetry as soon as possible. Then we just need to implement this on collision imminent. And so you can see here an example of responding to an event that has parameters. So these parameters are typed. There's just no need to like duplicate them here. Distance is a distance, position is an angle, and dimensions is a dimension. So what code do we want to write? So remember our satellite avoision code that we wrote before. So we kind of need a generic version of this. And so let's change our point of view here for a minute. So this is our kind of isometric view. Let's instead look straight down the vortex, right? Basically we're looking straight down the tube. So we can see the square here is the object that we might collide with. 0 degrees would be straight up, and so we can see there's an angle here that tells us what is the angle between the center and the object. So where on this circle is it? Now what we need to do is we need to move in the opposite of that angle. So move away from the object. We don't want to move to the object. We want to do it by enough so we can avoid the collision. And then, of course, we want to move back. So we need a generalized version of what we did before. Now, not to make things too simple, if the object is actually too close, there might not be enough time to react in this way. It does take time to move the vortex around, and if there isn't enough time, we won't be able to do that and we'll run into the object anyway. However, we can slow ourselves down to give ourselves time to move around the object. So there is another event we can send called adjust vortex speed and give it a percentage. So we can slow down by 90%, speed up by 110%, however it goes. So this is going to be complicated, and I'll let us see some more complex computation and timeline. So basically, if the object is too close, we want to slow down. We want to avoid the object. We want to correct our course back to where we were. And if we had to slow down, we want to speed back up so we arrive on time. Okay, so let's walk through this. It's going to be a little bit complicated here. So this is the general algorithm for just avoiding something in a general sense, right? So we have an adjustment. So how many milliseconds until we hit it? Well, let's do -2 milliseconds. That's when we'll do our first adjustment. We'll adjust back 4 milliseconds after that, right? Gives us 4 milliseconds to 6 milliseconds to get on the object. The direction would be 180 degrees offset from the position of the object inside the vortex. We'll see the slowdown logic in a second, but then you can see we're sending these vortex direction events. This looks kind of like what we saw before. And then you'll notice we send a ping at the very end. We do need to, once we've changed our trajectory, we do need to re-ping to see if there's anything in our path now. Okay, slowing down is a little bit tricky. So we decide that we're too close if we're less than 10 milliseconds away from colliding with the object. So in that case, we have all this extra stuff that's happening. We're going to slow down by 90%, speed back up by 110%. Notice a percent signs. Percent is a type. These are typed literals again. And then we're going to send adjust vortex speed to slow down. And then we'll speed back up after we're done. And after that, we trigger our avoision logic just as before. So there's a lot going on here, and I wouldn't worry too much about the specific logic, but I want to talk about some of the language features and anti-features that are in here. So first, I want to call your attention to this Boolean. So we notice that the Boolean ends in a question mark. Now, Booleans are special. In every programming language, Booleans are special. Why? Because Booleans control the flow of logic. If our programs didn't need to have alternate flows, they would be very, very simple. It'd be very easy to write programs if you didn't have to have branching logic or conditional logic. But you do need to do that, and Booleans are where that happens. And so in timeline, a Boolean variable has to end in a question mark to indicate that it is a Boolean and that it is special. So regular variables can't end in a question mark. Booleans have to end in a question mark. You'll also notice that we're reassigning the value of some variables that had been previously declared, and we're using a different syntax. Reassignment can create errors if you mistype a variable name or you use the wrong one. So we want to make sure that programmers are being very clear when they reassign variable names. Adjustment is now 1 millisecond. You can't reassign a variable by saying is, and you can't declare a variable by saying is now. So this forces you to acknowledge that you know that you're reassigning the value of variable and that you know what you're doing. You'll also notice this do nothing construct down here. So all if statements have to have an else. You can't have an implied do nothing else. You have to write the else. This forces you to think through, what do I want to do if the Boolean is true or if the Boolean is false? And even if you don't want to do anything, you have to acknowledge that explicitly using a construct of the language. You can't have an empty else that just has a comment in it. You have to say do nothing. So here's some features that you might think we could use that we don't have. So let's talk about expressions again. We do this all the time if distance less than 10 milliseconds, right? Why can't we do that here? That is not allowed, right? If statements have to be a literal or a variable. Similar arguments about density that we talked about before. But what happens is this means that every single expression is named in your program. And because the variable names have to be words that are defined in the dictionary, every single expression ends up being pretty well defined, and there's not much ambiguity in what bits of the code actually mean. This is actually a huge benefit. They talk about in a lot of programming languages, you should extract your complicated conditionals and expressions into a method. Yeah, you should, and in Timeline, you have to. Now, you might also think that we could get rid of some intermediate variables by making a more complex expression, 110% times distance plus 5 milliseconds. Well, this is also not allowed. Expressions can only be a thing, an operator, and another thing. You can't have nested or compound expressions, right? So we talked about density before, that's part of it, but this also creates a lot of complexity. We have to think about operator precedence, think about parentheses. There's just not a lot of benefit to it, and it ends up being a lot simpler if every single expression is just a few things, has a clearly defined name, and you build them up one step at a time. It makes it very easy to understand how the code evolves and exists and works. Okay, so we added some generic code to avoid an object that may or may not happen. Let's see how that did. Okay, 95% chance of success. That's pretty good. Depending on what's going back, I think we might like those odds. And you also consider that there's a 1.23% chance that the connection won't even be made in the first place, and we won't even be able to go. So that means there's a 96.23% chance that this trip will not result in anybody dying. That's pretty good. Now, we're not going to be able to fix any sort of hardware problem. Those are just not fixable. We just have to kind of tolerate those. So that leaves us with 2.77% chance of some collisions. How might we deal with this? How might we address these now? So we wrote our generic algorithm. I guess we could try making it more generic. It's unclear, actually. So what we need is more information. So now handling edge cases like this is where complexity lies. Like, we've handled the pretty basic things that are going to happen, but now we're going to be introducing some complexity. Now, unit tests are a great way to drive out some of the complexity we need to handle these edge cases. And an early version of Timeline actually did support unit testing. You could write a unit test of your event handlers, and that allowed us to drive very, very complicated, sophisticated algorithms to avoid lots and lots of edge cases. However, much like the machine learning algorithms that we initially used, the result was code that was too complex to understand, code that when it failed, we could not explain what actually happened or why it worked that way. It was too difficult. So we thought about something else. Instead, we thought, let's just focus on observability. Let's have real details about exactly what's happening in our code so that we can write exactly the kind of code that we need and not get too fancy. So in an airplane, there's this thing called a black box. It records everything that happens in the plane. They use it in investigations when a plane crash happens. So we can get a black box too. So we can tell the simulator, give us a sample of what happened during this particular failure mode, and let us walk through that black box to see what happened. The black box is incredibly detailed. It basically is a record of every single thing that happened, who did it, where it happened, when it happened, what values were given, right? We can see here, trigger was started by the Time Space Manifold, that we handled the start event on the first line. of our code, et cetera, et cetera, et cetera. We can see how we're scheduling events to be sent, and then later the time space manifold is sending them actually on our behalf. We can see the values that were being sent. So we have real observability. We didn't have to write any log statements. It's just provided by the runtime. So we don't have to do any extra work to get all this. The runtime handles all this stuff for us. Now, if we keep paging through and paging through, we'll see what the problem is. So at time index 127, we triggered a vortex adjustment. So it's probably to avoid something like our generic algorithm that we created. Then we can see at time index 128, we collided with something. So essentially, we adjusted ourselves away from one piece of junk and into another piece of junk. So not good. But now we have a failure mode. We could write code to deal with that. So what do we do next, right? So we ask ourselves, is this a risk we want to mitigate? Is this risk significant enough for the trip that we're trying to take, for the problem we're trying to solve, that we want to actually spend time mitigating this risk? Or are we happy with this risk? So we could write code to try to mitigate it if we really do, or we could just accept it. And accepting it doesn't mean that we go, it just means that we don't think there's value in mitigating the risk. So then we look at the overall risk profile and decide, do we want to take this trip or not? If I'm sending a bottle of rum through, I'm definitely taking this trip. 95% chance is pretty good. If I'm sending astronauts through, I don't know, maybe. Depends on what they're going through to do. So testing, right, can give us some assurance that it works the way we think it should work. But risk assessment, what we're doing, gives us confidence about what will actually happen, right? Because remember, the most important thing about a program is what it will do. The second is what it did do. So that is the beginning of everything that we've just talked about. Okay, a few takeaways. If you want to learn more about the timeline programming language itself, and we got a little bit of an intro here, but there's a lot more to it. You can go to timelinelang.com and check that out. But if you're not interested per se in time travel, like hopefully you can take something away about designing APIs, right? Consider the problem that you're solving when you're designing an API or a user interface or even a programming language. What is the problem that you're actually trying to solve? And solve that problem. Don't solve a bunch of imagined problems that aren't real or aren't important or that you aren't caring about. And think also about what it is that you value. Not every programming language values the things timeline values. And these values are what drive the decisions that we make. Think about what you value explicitly and make design decisions based on those values. So thanks a lot. My name is Dave Copeland. You can follow me on Twitter at DaveTron5000. And let me know if you have any questions.